Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video on tree diagrams. So tree diagrams are used in probability for multi-stage events that occur in stages, in order to list all of the possible outcomes and assist with calculations. So let's look at an example of where we might use a tree diagram. We'll start off with this example. Coin is tossed 3 times. What's the probability that I do not toss 2 heads and a tail? So this is a multi-stage event because we're tossing a coin 3 times. Each time I toss the coin is a new stage with a new set of outcomes. So we're going to draw a tree diagram to list all of the possible outcomes. So what we do is we arrange some columns for each stage of the multi-stage events. So here there are 3 stages, 3 columns, first, second, and third. So at each stage we list the possible outcomes. So when you toss the coin, of course, you can get heads or tails. At the second time, you can get heads or tails. And similarly for the third time, you can get heads or tails. So there's no real point doing this unless I list all of the outcomes. So to find the outcomes, I just follow the branches. So I have head, head, and then another head. So that's my first outcome. The next one is head, head, tails, and so on. So overall, the number of outcomes is 2, because there were 2 in the first stage, times 2 for 2 in the second stage, times 2 for 2 in the third stage. So 2 times 2 times 2, which is 8. Now in this case, all the outcomes are equally likely, so each of them will have a probability of 1 over 8. So then it just becomes about finding which of the outcomes satisfy what I was interested in. Do not toss 2 heads and a tail. So which of them are not 2 heads and a tail? Well, the first one's not 2 heads and a tail. And the same with this one. That's not 2 heads and a tail. And these 3 as well are not 2 heads and a tail. So the required probability here is just 5 out of the 8 outcomes. So this was a really easy example because at each stage, each event, heads and tails, was equally likely. But now we're going to look at some examples where at each stage the outcomes are not equally likely, and it makes the diagram a little more tricky. So a bag contains 3 red, 2 blue, and 1 green marble. 2 marbles are randomly picked, one after the other. What's the probability I pick the green marble? So this is a tree diagram question because the event occurs in stages. We're picking 2 marbles, one after the other. So the first selection is the first stage, and the second marble I pick is the second stage. So that's why a tree diagram would be appropriate. It'll help me list all of the possible outcomes. Now for this one, because I'm picking objects randomly from something, I need to know whether it is with replacement, which means that after I take the first marble, I put it back, I replace it with an identical object, or if it was without replacement, where I don't replace the first object that I pick. That will affect the probabilities. So we're going to firstly do this if it was with replacement. So here there are only 2 stages, 2 picks of the marble. So we have each time we could get red, blue, or green, and the second time we can get red, blue, or green. Similarly, red, blue, green. So then once again, we're going to write the outcomes. That's the whole point of doing the tree diagrams. We just write all of these outcomes. So we could get red, then blue, red, then green, and so on. So there are 9 possible outcomes. But this is not like the first example I did. I can't just say that the probability of each of these events is 1 over 9. That would be wrong. The reason that's wrong is not all of these are equally likely. For example, the first go, we're more likely to get a red than get a blue or a green. So because at each stage the events are not equally likely, what I need to do is draw branches for the first ones, and I need to write the probabilities on the branches. So for the first go, the probability I get a red is 3 out of 6, because there are 6 marbles, or it's equal to a half. And for blue, it's 2 over 6 or a third, and for green, it's 1 over 6. So because this is with replacement, if I pick a red the first go, that means I put back the red. It means that the probabilities of getting red, blue, and green the second go are the same as on the first go. It means on the second go, there's still a 3 out of 6 or 1/2 chance I get red, a third for blue, and a sixth for green. Similarly, half for red, a third for blue, and a sixth for green. So when you're picking objects with replacement, the probabilities do not change at each stage. Red is a half at each stage, blue is a third at each stage, and green is a sixth at each stage. So to calculate the probability of each of these events, what I do is I multiply the probabilities on the branches. So for red, its probability is a half times a half, which is a quarter. And of course, for red-blue, it would be a half times a third, which is a sixth. And then red-green would be a half times a sixth, which is 1/12, and so on. So yes, these probability calculations do take a while. So now I've listed all the probabilities. There's a couple of ways that I can sort of check that I'm on the right track. Firstly, it shouldn't matter the order of the outcome, the probability is the same. So what I mean by that is red, blue, and blue, red should have the same probability, and they do. So I know I've done something right. Similarly, red, green, and green, red should have the same probabilities, which they do. So I've done something right. Another way you can check you're on the right track is make sure that the sum of all these probabilities is equal to 1. I've checked it for this. They do equal 1, so I know I've done something right. So now that we've done this, we can finally get back to answering the question. What's the probability that I pick the green marble? So let's go through and highlight all of those ones that include the green marble. So I want to include this one, because it's got the green one, this one, and I want to include all of these 3 here. So that is 5 of the outcomes, but the answer is not 5 out of 9 because not all of these outcomes are equally likely. So what I do is I actually add up the probabilities of all of these events. So if you add up the probabilities of all these events, you get 11/36, and that is my answer. The probability I pick the green marble is 11/36. So what I want to do now is I want to change this question, so instead of being with replacement, it's without replacement. So we've got exactly the same question, but now the marble is going to be picked without replacement. Once I pick the first marble, I don't put it back or replace it with an identical marble. So actually, the tree diagram and the probability calculations are very similar. The only thing that's going to be different about my tree diagram are these probabilities the second time around. They will change because I'm not putting back the object I picked the first time. So all of those will change, which means all of these will change. So let's rub this out and put in the new probabilities. So here, now that it's without replacement, we still have the same set of outcomes and a similar looking tree diagram. The only difference is that the probabilities the second go around will change. So the first go around, there's still 6 marbles and 3 of them are red. So the probability I get a red the first go is still a half. So if I pick the red and don't put it back, there are going to be 5 marbles left. 2 red, because I've picked one and haven't put it back, 2 blue, and 1 green. So the probability I get a red the second go around will now be 2/5. Blue will be 2/5, and green 1/5. So similarly, if I pick the blue and don't put it back, there's 1 blue left, 3 red, and 1 green. So 3 out of the 5 left will be red, 1 out of 5 blue, and 1 out of 5 green. And similarly for the last one, green, if I pick the green marble, there are still 3 reds and 2 blues left, but there's no chance that I'll get a second green because there was only 1 to begin with. So once again, we figure out the probabilities by multiplying the numbers on the branches. So red will be a half times 2/5, which just gives me 1/5. So remember in the previous example, the probability I got 2 reds was 1 over 4. Now it's 1 over 5. So making this without replacement, the probability of getting 2 reds is slightly lower, because if I pick a red the first time, it gets taken away, so there's less chance of getting it the second time. So I'm going to go ahead and fill in the probabilities of the other 8 outcomes. So here we have all of the probabilities. Once again, I can sort of check I'm on the right track. I note the probability of getting red-blue is the same as getting blue-red, for example. I've also checked that all of these probabilities here add up to 1, so I know I'm on the right track. So once again, to find the probability that I get the green marble, I just go and find all of the outcomes that have the green marble, which are all these, and once again I add up their respective probabilities. The reason I'm adding is because this is an OR. I can get, to get the green marble, I can get red-green or blue-green or green-red or green-blue or green-green. And you know, when I'm saying what's a probability this or this happens, I add up their probabilities. Now, all of these 5 events that I've circled are mutually exclusive. So that's why I add up the probabilities. So it'll be 1 over 10 plus 1 over 15 plus 1 over 10 plus 1 over 15. And if you add all of those up, you get 1/3. So when this was with replacement, the probability was 11 over 36 that I got the green marble, which is slightly less than 1/3. Now the probability I get the green marble is 1/3. It's gone up a bit. And that's because the probabilities of getting things like red-red and blue-blue have gone down. Okay, so that's all there is to it. Make sure you know the difference between with and without replacement. So I'm just going to do one more example now that's kind of neither with nor without replacement. So let's look at this question here. The probability that the Brisbane Broncos win their match on the weekend is 0.7. Probability that Arsenal wins is 0.6. What's the probability that only one of these teams wins? So why is this a tree diagram question? Well, there are 2 stages here. The first stage we're looking at is the result of the Broncos match, and the second, the result of the Arsenal match. So there are 2 stages. Let's put up with Briz for Brisbane Broncos and ARS for Arsenal. So, for Brisbane, the options are win or not win. So note, we're only interested in whether only one of the teams wins. So we're only interested in whether it's a win or not a win, not whether it's a loss or a draw. Similarly for Arsenal, they can win or not win or not win. And this is what my tree diagram should look like. So once again, I want to list the outcomes. So the first outcome is they both win. Second outcome is just the Broncos win. Next, I have just Arsenal wins, and then I have neither wins. So this is not with or without replacement, because I'm not really picking something from a bag or anything like that. What we have here are sort of 2 separate events. The result of one game, and then the result of another game that has nothing to do with the first game. So once again, these outcomes are not equally likely, so I need to put the probabilities on the branches. So for the Broncos, there's a 0.7 chance they win, so that means there's a 0.3 probability they don't win. For Arsenal, the probability they won was 0.6, so it's 0.4 that they don't win. So once again, to find the probabilities of each outcome, I just multiply the respective probabilities together. So the probability that both win is 0.7 times 0.6, which is 0.42. The next one is 0.7 times 0.4, then 0.3 times 0.6, and 0.3 times 0.4. So once again, I can see if I'm on the right track by checking that these add to 1, and absolutely they do. So now that I've done that, I'm just going to find which satisfy what I was interested in, which of the 4 outcomes constitute only one of these teams winning. Well, not the first one, because that's both teams winning. Not the last one, because that's neither team. But these 2 here, they are events in which only one team wins. So the probability that this or this happens, again, they're mutually exclusive, I just add together the 2 probabilities. It will be 0.28 plus 0.18 which gives us 0.46, just under 50%. So hopefully now you see why tree diagrams are important. They just help us list outcomes and help us with probability calculations. So make sure you remember that if at each stage the outcomes are not equally likely, you must write the probabilities on the branches and you multiply those probabilities together to get the probability of each outcome. All right, thank you so much for tuning in. This has been the luckiest maths teacher in the world. Have a great day.